Hi. So let's do a lecture for the snow days, just so that we don't fall too far behind. So I'm gonna prove that term that I just vaguely mentioned last time. So that this idea of when is an operator on a vector space invertible in terms of the norm. Now this well, I call it a proposition in the book, right? It works in any vector space, really, with some slight modifications. But we're only going to do it for finite dimensional spaces because we're only interested in finite dimensional spaces. So let GLX as a subset of the linear operators on X, let this denote the invertible operators, so the operators that have an inverse. Now the naming GL comes from general linear group, because then you get a group structure on this on this set of operators where you have you can multiplication as the composition, and you get, of course, inverse, right? So you get a nice group over here, right? Now, X is a normed vector space, right? And what we'll have is that if we have an operator that's invertible, so an invertible operator on X, and an operator, another linear operator, we don't yet know if it's invertible, but what we do know is that it is close to A, and by close we mean that the distance in the operator norm, so whenever I'm applying a norm to an operator, it's the operator norm. So the distance between A and B is strictly less than, and that's important, than 1 over the norm of A inverse. We know that A is invertible, right? We're in a finite dimensional vector space. We can, all these norms are finite, right? We've proved that. So if we have this inequality, then B is invertible, right? So once you're close enough to an invertible operator in terms of the operator norm, then you are invertible, in fact. Now, that really makes, what does this inequality mean? It means that GL is an open subset, right? It gives you a very specific way to define these open neighborhoods, right? I mean, something is an open subset if near each point it has a neighborhood, right? So that's immediate from this inequality. Now, the main point of part 2 is that the inverse operation is continuous, right? So if thinking of it as a function on this this open set, right? I mean, it's it definitely takes invertible operators to invertible operators, right? A inverse is again invertible, right? And it's a continuous function on GL of X, where the metric is, of course, the operator norm. Oops, sorry about that. So, wrong button. So, hey, let's maybe pause a moment before proving it. Let's just see a place where the term is obvious, right? So consider when you have a one-dimensional vector space. And let's just look at R. So R1, right? So here vectors are just numbers, right? Single numbers, right? And what are linear operators on this space? Linear operators on this space are just numbers, right? It's multiplication by numbers. That's a linear operator. So if x is a number in R1, R vector, then a linear operator is just a times x. That's the only, right, an operator that goes back into R1, right? So So that's what the linear operators are. And it's fairly easy to see that the operator norm of the operator A, right? A is a number, but it also represents a linear operator, right? You can think of it as a one-by-one matrix. We'll talk about matrices in a moment. The operator norm is just the absolute value of A. Why is that true? Well, think about what are, right? I mean, the operator norm is sort of the maximum norm that you're getting when you're plugging in vectors that are exactly of norm 1. Well, in R1, there's only 2 vectors that are of norm 1, namely 1 and minus 1. So you just need to figure out what is A times 1 and A times minus 1. What's the maximum absolute value of that? Well, it's the absolute value of A, right? So the operator norm is just absolute value of A, right? So when is such an operator invertible? Well, it's precisely when this number A is not 0, right? Because then you just take multiplying by 1 over A is clearly gives you back, so 1 over A times X gives you X, right? Now, if you have that, what is this inequality in this setting? Well, A minus B, if I have B as another operator, right? So the operator norm of A minus B is, again, just the absolute value of A minus B. And it's strictly less than 1 over the operator norm of A inverse. Well, the operator of A inverse is 1 over the absolute value of A. So 1 over that is just the absolute value of A, right? So we get that A minus B in absolute value strictly less than the absolute value of A. Well, that is, that implies that B cannot be 0, right? Because if B was 0, then you would get absolute value of A strictly less than absolute value of A. That's nonsense, right? So that means that B has to be non-zero, means it's invertible, right? Furthermore, we have the thing that takes A to 1 over A is a continuous map, right? Because the operator norm is the absolute value, right? And so the metric on this is the exact same metric that we're getting with just the standard metric on the real numbers, right? All right. Now, if this is a slight typo, I should say dimension, right? So when the dimension is bigger than 1, there are other non-invertible operators than just 0. You probably remember that this is when the determinant is not 0, and it tends to become a little bit more complicated, right? So it's not, it's no longer, so simple. But we still get this this proposition over here, right? So let's prove this. So let's prove this in general for finite dimensional spaces for us. Okay, so let's start with 1, right? So let's prove that if we have this inequality, then B is invertible. Right. So what do we know something about? Well, we know all that we have. Well, we have that A is invertible, so A inverse exists, and we have this inequality over here, right? So we know something about A inverse and A minus B. So how about we just try something with them? We mess around with them. Well, they're operators, so we apply them to some vector, right? See what that does. And well, we have to combine them in some way. Let's just take A inverse times A minus B times X, right? Let's see what that does. Well, if we expand that, right, I get that's equal to X, because A inverse A X, right, just gives me X, right? And then I get minus A inverse B X, right? So what does that say? That says that if I add this guy to this, right, I just get X. So the norm of X, this is for any X in our vector space, is equal to this, right? Because that's what X is. Now, apply the triangle inequality, and then apply the inequality, right? If I have the norm of A inverse A minus B X, right, I can cut it up into the various norms, right? I can cut it up into the norm of A inverse, that's the operator norm. The norm of A minus B, that's the operator norm. The norm of X, that's the operator on the vector space X. Then plus, because I applied the triangle inequality. And over here, I do sort of the same thing. I do the operator norm on A inverse. And then I don't cut up this thing. I just leave it as the norm of Bx, right? That's, again, norm of X, because B takes X to X, right? It's a linear operator on X, takes X to X. All right, so what are we going to try to do? We're going to try to prove that if X is not zero, then B of X is not zero, right? Because that's going to imply that B is 1-to-1. So assume that X is non-zero, right? That means that the norm of X is non-zero, right? And it's an if and only if, because that's a norm, right? Now, if we take this inequality, norm of X is less than or equal to this expression, and we apply the inequality over here, right? This inequality over here, right? The one that we know something about, right? What do we get, right? We applies to A minus norm of A minus B. So this becomes, so I get a strict inequality. I get a strict inequality because the norm of X is not zero, right? And this A minus B is strictly less than 1 over A inverse, right? And I do get a strict inequality again because norm of X is non-zero, right? Otherwise, this whole thing would just be 0 and we wouldn't get a strict inequality. Right. So that means we get, so in this first term, that just becomes X, and we get a strict inequality. And I don't do anything with the second term, right? So that's how I got this inequality over here. Now, if you look at it, you notice that this bx over here, cannot be 0, right? If it were 0, then I'd get norm of X is strictly less than norm of X. That's nonsense, right? That can't be, right? So that means that this bx cannot possibly be 0. Whatever it is, it's not 0, right? So that means that norm of b of x is not 0, right? For all non-zero x. That means that bx is not 0 for all non-zero x, right? It's not the 0 vector, right? Because the only vector whose norm is 0 is the 0 vector. Now that's enough, as we've seen before, that to show that b is 1-to-1. Because if b of x is b of y, then we just do a little bit of algebra, right? We have that b of x minus y is 0, and that if we have, right, if the only thing going to 0 is 0, that means that x minus y is 0, so x equals y, right? So that means that that we have that b is 1-to-1, right? So b is, that's not quite yet enough to have invertible. We need onto, but it's in this case it's easy because we're in a finite dimensional setting, so we have the rank nullity, right? If we have an operator, it's on a finite dimensional vector space, taking the vector space to itself, it's 1-to-1 if and only if it is onto, right? That's the rank nullity theorem, right? Or one version of it, right? So that's exactly the statement that we proved. All right, so that proves 1, right? Because once we have 1-to-1 and onto, it's invertible, right? So we've proved that makes it actually a linear operator, right? And once we have a 1-to-1 and onto linear operator, we've proved that the inverse is actually linear, right? So we're done, right? Well, with part 1, right? So let's prove part 2, right? So we've already said that part 1 immediately implies that GLX is open, right? So let's just assume it's open. Let's prove the this thing about the continuity, right? So suppose that we have some invertible GLX, right? Some invertible A, sorry, in GLX, right? So, so what we're going to try to do now is that we're going to look at, we know that we have a whole neighborhood around. And so we're going to try to do, we're going to apply the inverse, and we're going to try to see if what's the limit, right? So again, we're basically going to show that in a sufficiently small neighborhood of A, the inverse is Lipschitz. Now, for that, we don't want to take the entire neighborhood from part A, because it wouldn't be Lipschitz in that neighborhood, right? Really, because as you get close to the boundary of that neighborhood, the operators start becoming non-invertible, and then things would go to infinity, right? So what we're going to do is we're going to assume. Actually, let me stop here. The cat is trying to destroy the door. All right. So sorry about that. So the cat needed a little bit of yelling at. All right. So let's whenever there's nobody in the house, or they're bored, they try to destroy stuff just to get attention. All right. So let's. So where were we? Oh yeah. So we're looking at this inequality, and notice in particular that I put a 2 here. So I'm really looking at half of the neighborhood that we were looking at in part A, right? I'm looking at half the ball around A, right? Rather than going up to 1 over the size of A inverse, I'm only going up to half of that. Now, the half is not anything really important. It's just any number less than 1 will work, any positive number less than 1. Now, if I choose something that's closer to 1, the estimate that I get in the end is going to be worse, but it's still going to be Lipschitz, it's just with a bigger constant. So notice the 2, right? That's important. So, but one thing is, this is definitely still less than 1 over norm of A inverse, right? So that means that the estimate from part 1 is still satisfied, right? The estimate without the 2, right? And so B is invertible, right? So we can apply, we can write down B inverse, right? We know that B is invertible, right? 1 holds, right? So, all right. So now we do basically the same. So the first computation, we look at the same thing, except now instead of sticking in X, we're gonna stick in B inverse of Y, right? So above we essentially did this thing just with X, but we're gonna stick in B inverse of Y, right? So that's what we do here, right? And now we have a different estimate for for the norm of A minus B. In particular, we have that it's less than this guy, right? So let's apply the. This is really a strict inequality, but who cares? If Y is not 0, it would be strict inequality. It's if Y is 0, then this could be equal, right? But it doesn't. We won't really worry about it. It doesn't really matter. So we get that this guy is less than or equal to this guy, right? And that 1/2 is precisely because of this 1/2 over here, right? Now that's important, right? We want to have an estimate of this guy in terms of this guy, right? Now this is a fairly typical way to estimate things. If you have this is less than or equal to something smaller than 1 times this plus something, well, we could take this guy and just subtract it from both sides of the equation, right? And we're gonna get that half of this, because we subtracted half, is less than or equal to this thing. All right. Now, we'll write it in a slightly different way. We'll multiply by 2 to really get an estimate for this guy in terms of this, right? So that's what it is, right? That's what we got over here. Now, what does that mean? Right? This was for all y, right? As we saw, in this basically tells us something about the operator norm of B inverse, right? B inverse of y is less than or equal to some number times the norm of y. Well, that's some number, right? The smallest such possible number is the operator norm, right? So if we have this thing for all y, well, we don't quite know the operator norm, but we know that it is at most this, right? So we get this estimate over here for the operator norms of B inverse in terms of A inverse, right? And again, you wouldn't get this if you went all the way up to boundary over here. If that 2 wasn't there, basically the number that you get over here, that's 2 over here, that's not quite just the reciprocal of this thing. It's reciprocal of 1 minus, right? And so that would go to infinity. So if you have 1/2, you get this. If you'd want to have even better one, you'd take maybe 1/3, right? If you want a worse number here, a bigger number, you maybe go to 3/4 or something. You can figure out what it is, right? Then you get for 3/4 you get 4 times. But it doesn't really matter. We're not interested in the specific estimate. We're just interested in that the inverse operation is continuous, right? So you really want to, we really need to bound this thing, right? Figure out as B moves about in a neighborhood of A, what is happening with B inverse minus A inverse, right? So, so for that, we want to basically we want to know something about this, right? And we know something about A minus B, A inverse, and B inverse, right? So let's write down. This is a fairly typical thing, right? Write down B inverse minus A inverse in terms of those 3 guys, right? It's just a little bit of algebra, right? Right. So this is just doing that. Like it's 2 distributions, right? So. All right, so we have that the norm of this is the norm of this, right? So norm of this is the norm of this, and then we apply, so these are all operator norms, right? That we have less than or equal to, well, the norms of these 3 guys, right? Now, what do we worry about? Well, A minus B, a norm, that's the thing that's going to 0, right? If we're talking about continuity, right? So that's good. We want this thing to go to 0 as A minus B, the norm of A minus B goes to 0. A inverse, that's just some fixed constant. That's not moving, right? It's the B inverse that's moving, right? This is where we're gonna, so if you didn't know anything about A and B, you wouldn't be able to say anything, right? Because you don't know what's happening over here. That might be going to infinity. But it's not going to infinity. That's what we proved, right? It is actually bounded in terms of some constant, right? A is fixed, right? The point where we're trying to show continuity is fixed. And we have that this is bounded by 2 norm of A inverse. And so we get 2 norm of A inverse squared, right? Because we have 1 over here and 2 times one of those over here. So we get this, right? What does it mean that, oops, sorry, wrong button. So what it means is that on this neighborhood over here, on this ball around A, I get this estimate, which means on that ball, it's not quite Lipschitz, but it satisfies the Lipschitz estimate at A, right? So, all right. So that means it's continuous, right? Because as A minus B goes to 0, this is just a constant, right? So this goes to 0, therefore this goes to 0. That's continuity. All right. So as B tends to A, this guy tends to 0. That means that B inverse tends to A, right? So it's basically restating the same thing, right? Inverse is continuous. Okay, so that's that theorem, right? So now you know how to if you have the, it's very useful in terms of if I have a linear operator, I can find nearby linear operators which are also invertible. All nearby linear operators are invertible. So I can move an invertible linear operator and it stays invertible. And how far I can move it depends on the norm of the inverse. All right. And you can use this if you need a little bit more information. You can use the basically the proof here, right? How do you get a bound on maybe the size of the inverse, right? All right, so that's that. So we know about how to test. Test. It's only one Drake. I mean, of course, there's other invertible operators further out, but we at least know that there's a near each invertible operator there's a ball of invertible operators, and we actually have a nice precise bound on the size of that ball. All right. So the thing that you probably have seen in linear algebra is matrices, right? And so if we we started with linear operators, so we're sort of doing it in sort of maybe the inverse order than you've seen it before. But I would think this is actually probably the correct order, right? Because really we're interested in there's lots of vector spaces. Not every vector space is Rn. Even finite dimensional spaces, they're not all Rn. And it's very limiting to always think as everything being Rn. So you don't want to always think in terms of matrices, because what matrices are basically representing linear operators in terms of fixed bases on vector spaces, right? They're basically, even on Rn in some sense, they're basically representing the linear operators in terms of the standard basis, right? And even including the ordering of the basis, right? And it's not the bases of a lot of vector spaces are not natural in any way, right? You can easily change bases, and that's what a lot of linear algebra is looking for a lot of differential equations, lots of all sorts of in all sorts of subfields of mathematics, right? You're looking for a good basis, right? And in infinite dimensional spaces, you can't even write down linear operators as matrices. I think I mentioned this before. I mean, if you have an infinite dimensional space and you want to do this sort of algebraically, it's the basis is uncountable, the so-called Hilbert basis. So how would you write down a matrix with uncountably many rows and uncountably many columns? It doesn't make any sense. And even there's some you can do some things in terms of matrices for some infinite dimensional spaces, but it's yeah, it gets a lot more complicated. It's not all about matrices, even if you could sort of write down some sort of infinite by infinite matrix. And anyway, so it's not yeah, that gets very, very complicated in infinite dimensional spaces, and there you definitely don't want to think in terms of matrices at all. All right, so how does this work? Well, suppose that we want to describe L of xy, where x and y are some finite dimensional spaces, right? So we have we fix bases x1 through xn on x, and y1 through ym on y, right? So you fix those, right? You have to to represent a linear operator as a matrix, you have to fix bases first. If you're going to do different bases, you're going to get different matrices. All right. So, well, how do you represent the basis? Well, a linear operator, you know the entire linear operator once you know what it does to a basis, right? So you really only need to figure out what it does to the basis elements, right? So you basically look at what what a of xj, right, where xj, x1 through xn are the basis elements, right? So you look at what a of xj are, right? Those are elements of y, right? And I can write them down, right? I can write this a xj in terms of the basis of y, right? So for any fixed j, right, I defined numbers a1j, a2j, all the way through a mj, right? And that gives me a representation of what axj is, right? And I do this for every j, so I have a matrix of numbers, right? That is, sorry about it. It's it's a phone, but it's probably some okay, probably some spam. It's from Brunswick, New Jersey, or something. All right, right. So where were we? Okay, so we get this matrix of numbers. And so sometimes you write A. Sometimes if the numbers themselves are important, we write the matrix for short as this, because you don't always want to write down this entire big thing, right? You say, well, I'm going to have a matrix where I call A, I, J, and the various entries in the matrix. It's in linear algebra you always do rows first, columns second, right? So the first number is the number of the row, the second number is the number of the column, right? This is slightly different from if you do some sort of computer programming and you have a sort of for example putting stuff on the screen. It's often inverted, and actually, in the, let's say, the XY coordinate system, right? On just on R2, let's say, it seems inverted as well, right? So it's first is the the column, second is the row, right? But so here we do row first, column second, and that has a good reason. It's not just making it complicated. That has a good reason to make the computations easy. All right, so so that is an M by N matrix, rows, columns, right? So you have M rows, N columns, right? And the columns are of this matrix, these guys, right, are precisely where the jth column is precisely the representation of AXJ, right, in terms of the basis on Y. And if we know these numbers, then we can compute the linear operator, right? Because we know how to represent it on a basis, and we know that once you know a linear operator on a basis, you know it everywhere, right? So, all right. So a matrix gives a linear operator gives a matrix, as long as you have fixed bases, right? Your bases are fixed a priori. You're always doing everything with the same basis, right? And of course, the problem is that often it's, the bases are not really sort of naturally in any, they're kind of, they depend on your mood, right? They're not sort of, given a lot of times, right? Okay, so now let's look at this a little more. So if we have, let's see how it behaves, right? So suppose that you have z, a vector z, which is given in some, in the basis x1 through xj, right? So it's given by these numbers cj, right? And let's apply a to it, right? So if we apply a to z, what do we get? Well, a to z, well, it's linear, so we can just take the a inside here. Well, we know what axj are, right? That's this expression over here without the cj. So then what we could do is I could sort of rearrange terms a little bit, move the m out, the n in, right? And what I get is this thing, right? So I get an expression for for these are the coefficients, right? If I'm writing az in terms of the bases y1 through ym, right? And that's the sort of the familiar matrix multiplication. In this case, it's the multiplication of a matrix and a column vector, right? So the matrix is aij and the column vector is cj, right? So, right. I did say this. Now, if we have two matrices, A and B, and we could multiply them together, right? So maybe a B would be an n by R matrix, and with these entries, right? So that we can, so it's a matrix that goes from R, right, the R-dimensional space to the n-dimensional space. So we can multiply it, right? We get C, right, which is just AB, right, and because we just, it is a linear operator, AB, right, works. So if we have that, we get this formula, right? So and that's the familiar formula for matrix multiplication, right? And one way to remember, and this is where the row column order comes in, is that basically A times B, I'm just multiplying the entries, and if I order them in this way, right, then notice something. It's the J. Sorry, it's maybe. Let me. Me do just right. It's the J that sort of disappears in this guy, right? It's sort of sometimes people say it's summed out, right? So it's Aij, Bjk, right? And it's the J that sort of gets cancelled in some way, right? And we're summing over the J, right? So the J goes from 1 to n, right? So it makes it sort of easy, right? Because I have CIK, so the order is IK, and you can see that, well, those are the outermost elements here, right? And if you had more matrices, you just, again, order it this way, and always the inside guys get canceled out, and it's the outermost guys that give you the final matrix, right? So actually, remembering the formula in terms of the coefficients is actually really easy once you realize that this is the way that the ordering row column works, right? All right. So by the way, maybe something I didn't quite mention, so strongly. It's this, and that deserves a remark, right? It's a matrix is something that works on tuples of numbers. It's something that you can think of as sort of directly representing linear operators on Rn in the standard basis, or it's something that just sort of formally takes n tuples of numbers. Gives you other n tuples of numbers, right? It takes column vectors and gives you other column vectors by basically this formula, or maybe this formula, right? So it's something that works on n tuples of numbers, not necessarily on vector spaces, right? If you want to work on vector spaces, you have to fix bases, right? You could say standard basis on Rn, but you could have different. Even on Rn, it's possible to have different bases for different for different problems. You might want to use a different basis, right? So if you do have a different basis, what is happening here, right? I mean, it is changing the matrix. Now, what? How does this change? Well, you can take, if you have one basis and you have another basis, then you can have a linear mapping that takes, right? I mean, you can just say, well, the first element of the first basis goes to the first element of the second basis, right? And so on, right? That gives you an invertible mapping, actually, right? You define it on the basis and then you extend linearly, right? So you always get, whenever you have two different bases on a vector space, there is a matrix that takes one to the other, right? That's the change of basis matrix, and it really just basically look at the columns. You're representing one basis in terms of the other, right? So that you can always go between bases, right? And that's where things like similarity, if you remember from linear algebra, comes in, right? You were looking at things up to similarity, right? Looking at matrices up to similarity, and that's basically taking matrices and seeing what they are under different bases, right? So you could you maybe try to diagonalize a matrix, stuff like that, right? So if you change a basis, what happens to the matrix? That's applying these change of basis matrices. All right, now let's sort of now specialize to Rn and Rm, and prove something about it's a lot of times the reason why you use matrices is that it gives you a way to compute something, right? I mean, I can describe a linear operator in terms of numbers, right? So in this case, L of xy, I can describe it in terms of n times m numbers, or n times n, right? I can describe it in this matrix, right? I have finitely many numbers. They describe the thing, so it can give me sort of like a coordinate system for my operators, right? Now, if we want to talk about, let's say, continuity, well, it would be nice if we could figure out what is if we have, let's say, continuity in terms of the operator norm, what does it mean in terms of these coordinates, right? And they are related. It's not that if I take the r n times m, this guy over here that we're going to talk about, it's the standard Euclidean norm is not on that guy is not the operator norm, right? But we do get at least one direction. So if we take, let's look at same z, right, as above, right. It's in terms of the Cj, and we look at the norm of az squared, right. So these were the coefficients, right. So we square them and we sum, and we're taking the square so that we don't have the square root here, right. So that's the reason for the square over here, right. Now, once we get this, we notice that this inside here, that's just an inner product, right? I mean, in some sense, if we're looking at matrix multiplication, right? I mean, if you're multiplying two matrices, it's basically doing a whole bunch of inner products, right? You're taking inner products of rows with columns, and for that we have Cauchy-Schwarz, right? So we can take this inner product, right, and estimate it from above by the norms of these as vectors, right? And that's what this is, right? Nice. Right, the square takes out the square roots, right? So this is really the inner product squared, so that's why I don't have square roots in there, right? Again, that's the reason for putting the square out here, is to avoid all these square root signs. So I have this. That's Cauchy-Schwarz, showing that that's less than this. And now, once I'm here, what is this thing? Well, that's just the norm squared of z, right? So that's just writing it in a slightly different way, right? But it does give me something. Now I can take the square root of everything, right? And I see that the norm of az is less than or equal to the square root of this number, right? That's what I have over here, right? So it's not quite an equality. It's not going to give you an equality in general, right? Sometimes it might, but it's not going to, in general, give you an equality. But it gives you an upper bound, right? So basically, if you take the matrix, square all the elements, sum it up, and take the square root, well, that's exactly the norm, the Euclidean norm, or on R n times m, right? It's exactly how you'd compute the norm in there. It's not the same as the operator norm, but you get this inequality. So if you can bound the Euclidean norm on the space of matrices, right, you can bound the operator norm, right? So that's useful. That means that if, let's say, the entries of a matrix go to 0, or maybe like if I have two matrices, right? If I subtract them and the entries of the subtraction go to 0, right? So if the entries of a matrix go to 0, then the operator norm of A goes to 0. That means that A goes to 0 in the operator norm metric, right? In the topology of the operator norm. So that means that if I have a continuous function from any metric space S to Rn times m, sorry, right? So if I have a matrix whose components are continuous functions, right? Then I can think of it's a different mapping, right? I can think of f as a mapping from S to the linear operators from Rn to Rm, which that space has the operator norm, right, rather than the Euclidean norm on the original one, right, and that is still continuous, right, by this estimate over here, right, because if the difference in Rn m goes to 0, then the difference over here goes to 0, right, because I get that the operator norm is bounded by the Euclidean norm. So we've proved that half of this proposition, this next proposition, but it also goes the other way. If we have a continuous function into the space of operators, right? So from any metric space S, I have a continuous function that gives me linear operators. If that's a continuous function, then the entries of the corresponding matrix are also a continuous function. So that doesn't follow from this estimate, because that only goes one way, right? Just because norm of A goes to 0, this doesn't say anything about what happens to the Euclidean norm, right? And that's basically what we'd want. But it's there's a different. You can do a similar estimate going the other way around with some constant, but let's do it in a sort of simpler way. If we have this function that's a continuous function into the linear operators, that means that for any x in S, I have f of x is a linear operator, right? That means I can, and everything in terms of the standard basis, right? That means I can apply it to a basis vector, right? Because it's an operator. It's a linear mapping from Rn to Rm, right? So I can stick in something in Rn, right? This Ej, right? And I can see what that does, right? So that's what I do here, right? And that has to be a continuous function, because if I look at a continuous function of x, right? So a continuous function on S and valued in Rm, right? Why? Well, look at the difference, right? If I evaluated x and evaluated y, well, f of x and f of y are linear operators, so I get this thing, and that I can bound this norm over here. I can bound by the difference in the operator norms, right? Because the norm of Ej is 1, right? The standard basis, the standard Euclidean norm of a standard basis element is 1, right? So I get this inequality over here. That means that as f of x minus f of y, as that goes to 0, right? I get that this goes to 0. Now, f was a continuous function, so that means as x goes to y, so as x minus y goes to 0, then I have that f of x minus f of y goes to 0 in the operator norm, and I've just proved that means that this goes to 0, right? So that means this guy is a continuous function of x. All right, so if if we have right, so if we have this function, if we look at it, what are the components here, right? I mean, it is a function from S to Rm now, right? And it's the this thing is valued in Rm with the Euclidean norm. So now we have now we're no longer talking about operators, right? Now we have a function from S to Rm, where Rm has the Euclidean metric, right? And when is such a function continuous? Well, such a function is continuous, we proved last semester, right? Is if and only if the entries of that function, the components of that function, are continuous functions, right? And what are the components? Well, this guy is right? I mean, what is it? I mean, this is it's basically this column vector, right? So it's the those are the entries in the jth column, right? And so we know that those guys are the entries in the jth column are continuous, right? Well, that works for any column, right? So we have that if the mapping from S to the jth column is continuous, then and it's for any j, right? That means that the mapping from S to any entry is continuous, which means that that this guy is continuous. Again, sort of using that in reverse, right? So now I have, n times m continuous functions, and that's that gives a continuous function into R and M using the Euclidean metric, right? So basically, that's going to be useful because we're gonna want to take our notion of differentiation in several variables as linear operators, right? So a derivative of a function is a linear operator. So if you have a function between Rn and Rm, the operator is the best linear approximation at a point, right? And we really need to know when is this continuous, right? And the right notion of continuity of the derivative is the operator norm, right? And with this proposition, we see that